So we've talked about different integral techniques, and we've talked about the idea of things like trigonometric substitution and integration by parts. And what I want to talk to you a little bit today is an additional technique. But first, before we get there, let's talk about some of the ways you could solve integrals and whether or not that's a good idea. So, for instance, if I want to find the integral 1 over x squared minus 5x plus 6 dx, using the techniques that we have now, there's really only one way to do that, and that's trigonometric substitution. The problem is, if you recall from the way we've done trigonometric substitution so far, usually it's already in some sort of something squared minus something squared, like the squared terms are already there. However, that's not the only way you can get there. And in fact, sometimes this is kind of the way you have to do it. So let's walk through this. So the first thing we would have to do, we want to get that into something that trigonometric substitution understands. So we have to complete the square. Now, we talked a little bit about this before. You take this, you take the term in front, you take the middle term, you cut it in half and square it, or you cut the coefficient in half and square it. So we have negative 5 over 2 squared, but you don't get that for free, so you actually have to, you're basically adding 0. You're adding it and then subtracting it to make sure you're not unbalancing the equation, or the expression. But this right here, by construction, we did this on purpose, generates that x minus 2 quantity squared. Now you can multiply that out to figure that out. If you do the FOIL method, you'll notice you're going to get this. And then this is negative 25 over 4. This is positive 24 over 4. That simplifies to negative 1 over 4, which then you can represent as 1/2 quantity squared. Now the reason we do this is because now we have something in terms of a squared minus a squared. However, even then we're not really in that trigonometric substitution method. We could use trig sub here, but it would be kind of complicated. So we're going to use a simple u sub of u equals x minus 5/2. That gets us, now we finally have something in terms of, u squared minus sort of an a squared, right? Then we can set up the triangle. We have the 1/2, the square root of u squared minus 1/2 squared, and then a u here, right? That is our triangle. So then we can say, okay, if I have a triangle that looks like this, theta being equal to, or using a secant theta substitution seems reasonable. So what we're going to do is u equals 1/2 secant theta, right? Because secant theta is u over 1/2, so multiplying over u over 1/2 equals secant, so multiplying over that 1/2, we get u equals 1/2 secant theta. Then by differentiation, du is 1/2 secant theta tangent theta d theta. Right, so we're just going through trigonometric substitution. Hopefully you feel comfortable-ish with this. So we take what we had before, we substitute in everything here. Now what happens, I did a little bit of hand waving here. If I multiply top and bottom by 4, the 4 cancels with the 1/2 to get 2. And then on bottom, that 1/2 squared and this 1/2 squared are both 1/4. So that 4 on bottom sort of takes care of the thing, takes care of the coefficients down there. We have secant squared theta minus 1. Now we know that secant squared theta minus 1 is equal to tangent squared of theta. That's one of our identities. So we can reduce this to that. And then we'll have a tangent on top and bottom, so one of those cancels. And then we would have to convert to sines and cosines. If you do that, you have like a sine over cosine and a 1 over cosine. So the cosines disappear, so you end up with d theta over sine theta, which is cosecant theta d theta. And then you probably don't remember, but the antiderivative of cosecant of theta is the natural log of cosecant theta minus cotangent of theta, absolute value there, plus c. Then this is getting kind of nasty, right? Because now we're in thetas, but we didn't start in thetas. We actually started in x's, but we got to go back through u's. So I have to go here, I have to look at this triangle, and I have to say, okay, well, cosecant theta, if sine of theta is this over that, then cosecant theta is this over that, so we're here, and then cotangent theta is adjacent over opposite, so we have this, and then you do plus c. Now we actually have to say, okay, well, u equals 5, or x minus 5/2. once I plug that in, and I'm going to omit that because that's just algebra. I hope you feel comfortable-ish doing that. You bring it all together and then do some log rules, and you'll get natural log of x minus 3 minus natural log of x minus 2 plus c. So it actually cleans up to a fairly neat, like, tidy, I guess is the word I'm looking for, fairly tidy antiderivative. But we had to do a ton of work to get there. So the question is there a better way? And the answer is absolutely. So if you take a look at this, and we just factored it. So instead of doing all of that completed the square, what if we just factored it? So I factor this into 1 over x minus 3 times x minus 2. And what I find is that I can actually split this into that. Now this doesn't always work. If this was x minus 3 and x minus 10, for instance, it wouldn't just be the first one minus the second one. It doesn't work like that. It just happens to work in this particular case. So if I did this, I said, okay, I factor it and then I split it out. So I take this, okay, well that turns into the split one. Well, I can get the antiderivative here with a log rule, or with a u substitution and then the antiderivative, a u substitution and the antiderivative, and I get the same answer with a lot less board work. So you might ask yourself, how in the world do I do this? And the method of doing this is what's called partial fraction decomposition. It's an uncommon method. It's not used as often as it probably should be, and it's not taught with as much time and depth as it probably should be in a standard pre-calculus course, because it's kind of weird to understand, but it's a fantastic technique for being able to split your fraction into separate fractions. And separate fractions are really easy to deal with when we're talking about integrals, because you can go straight from something like this to something like that. And so we're gonna review partial fractions, review what we need to do to solve them. But I wanted to do this to kind of motivate us as to why this is important. And the answer is trig sub is nasty, so we try not to use it if we don't have to.